I give you this table, the student table, and I give you some numeric values for that table, and I'm asking you to just do the cost analysis for different major operations on the database, equal the full scan of all the tuples, file scan, equality search, and range search. And we need to actually use this information given to us to calculate the cost in numeric values. Okay, so that is what we will do. And we are going to kind of write it down on the side. Let's actually do it over here. Okay, so now let's first understand, we need to first understand the information that is given to you. So this table has 4 attributes: SID, SNAME, major, and email. So SID is the primary key, which means all its values are unique. And it says that SID values uniformly distributed between 100 and to this number. So uniform distribution means when you look at the SID values, when you actually split, let's say, tuples into, you take all the tuples, come up with buckets with same number of tuples in each, you will probably have same number of tuples in each bucket because SID values are uniformly distributed in the table. So it says that all attributes have type character 40, fixed length attributes, and each one's size is 40 bytes, which tells me that for each record, the record size will be, since there are 4 attributes, 4 times 40, which is 160. Okay, so this is the size of the size of each record. So it says also that there are total 100,000 records. In the table, block size is 16K plus 8 bytes. 8 bytes is for the reference, for the pointer to the next page. So that means we will store the data only in 16 kilobytes. Then also we need to assume that time to read and write a page is T. That's already what we assumed in our cost calculations before. And we will assume that each record pointer size is 8 bytes. And we assume that 1 kilobyte is equal to 1,000 bytes. So from this information, the first thing you need to do is, this is needed for everything, calculate the value of B. This is the most important and crucial, and the first thing that you need to do. So how can we calculate B? The number of pages that we need to store this data, this student table, on the disk. How many pages we will need? And assume that we don't do any file organization. We use a heap file. There won't be, it will be randomly ordered. How many pages we will need?
1,000.
Each record is 160 bytes. It's fixed. And why 8 bytes? Okay, let me write down the formula you mentioned. So total, we have 100,000 records. That means we have 100,000. So it will be like this. No, it will be 16 million, right? So it will be 16 million bytes total for the complete data. So for that 16 billion bytes, how much data can I store in each page? 16 kilobytes, which is 16,000, right?
16 times 1,000. Doesn't matter.
So I'm making assumptions. It's not, you are assuming that 1 kilobyte is equal to 1,000 bytes. So this will be equal to around 1,000 pages, right? Okay. So this is canceling, but around 1,000, we need 1,000 pages to store all the data. So now let's move on. We know what the value of B is. So we are assuming that in part A, this is what we are asked. You need to assume that you have a B plus 3 index on this data, on the student table, and in this table we built the index on the SID values, and we perform first a file scan. What will be the cost of file scan on this table?
1000.
So I get this data, which can be, if it's a heap file, it can be stored in 1,000 pages total. And I take this data, organize it as a B plus tree, clustered B plus tree, which means I store my index entry is 160 bytes. I store the tuples themselves, full tuples, full records, directly in the index.
1,000 pages.
Okay.
We measure it in how many times we have the disk access.
That is true. That's what we need to count. But remember, let me go back to that slide. We did some cost estimations. You need to use this information that we actually kind of derived here. There we go. So in B plus tree, since we make an estimation that there will be some empty space, we actually estimated that the data, because of some empty kind of space in each leaf node, it expands to 1.5 times the original the number of pages. Okay, so then, and this was based on this assumption here, 67% occupancy. And in the question, if you looked at it, it says us the same thing. It says that assume 67% occupancy for the B plus tree. And the kind of the height of the B plus tree is 3. I give you a lot of information already so that you don't need to do the calculations yourselves. So if I store the data in 1,000 pages in a heap file, if it is a B plus tree, I need to multiply that value by 1.5, it will be 1,500. 1,500 pages in the unclustered B plus tree. So what is the cost of the second operation, which is the equality search? And our assumption, it's actually the equality search is performed on the SID value 25,700. Since SID is the primary key, how many tuples will the result return? Just one. SID is the primary key. Okay? So now when I search the tree, what is the cost of the equality search? Let's say this is my tree, and the question tells me that the height of my tree is only 3. There are 3 levels, including the leaf pages. So these are the leaf pages. Okay. So, and it has 3 levels. When I search through, I need to read the root page, then a page in the second level, whatever the condition is, and then I will go to a leaf page and I will read it. There is a single tuple, and that leaf page will include that full tuple. How many page reads do I need to do? As much as the height of the tree, which is 3. Okay? So this is kind of for the, since I know there is a single, that's why a lot of database management systems just create indexes on the primary keys. If there is a single tuple that satisfies the condition, rather than scanning through the whole thing, it just gives you that only in 3 pages. And a lot of times, these intermediate pages are stored in the memory. It just loads them to the memory. There is a lot of memory. Today's computers have a lot of memory, and it will reuse these pages over and over. So it will be just reading the leaf page, the data page, most of the time. So, so the kind of the cost is actually, the answer to this is, for the second one is just 3. And if you actually multiply them with D, actual value, okay, there's an extra 0 here. This is 1,500 D, this is 3D. Okay, so let's actually move on to the third one. In the third one, I'm asking you to repeat the same thing for the range search. For the range condition, SID value less than 25,700. So it will be, if we go back and look at the table, this table, for the range search, I need to include the search for finding the upper bound, lower bound of the range condition. Then I need to find out the number of matching pages, and I will add those 2 together. Okay? So which means in my search, what I need to do is start in the root, search through. I'm looking for the lower bound of the range search. let's say that this is the one that has the lowest value in the range, and I need to keep reading the pages until I reach the upper bound, or until the end, actually. In this case, it's saying that it's less than 25,700, so we will go here in the beginning, and then we will just read these until we reach to the kind of this value. So the tricky part here is finding the number of matching pages. How can I find the number of matching pages? Here. So I know I have 1,000 total in the data pages. I have total 500 pages, right? Those are the number of data pages. And this is for how many tuples? Total 100,000 tuples. And this is for the range of values with this value. So the SID values range between these two values. So SID values from 100 all the way up to 204,900 are occupied in 1,500 pages. What I'm looking for is the range from 100 up to 25,700, right? So this is the range condition. This is specified in the range condition. Okay? Does everybody agree with me? So if to store all the SID values in this range, I need 1,500 pages. To store them, what I need to find out is to find out the SID values in this range, how many pages will I need? And I'm told that there is SID values are uniformly distributed in this file, right? So I can calculate this through proportions then, since it has uniform distribution. So what should be the formula for the distribution? For the proportion? I will actually multiply these two values. This is if I subtract, let me write down the full equation. 25,700 minus 100 times 1,500 divided by 204,900 minus 100. Okay? So if you do the math, you will see that this number is 8 times of the top number, so this will cancel and this will be 8, which means we will have 1,500 divided by 8, which is roughly around 187 something. I would say I will round it up, 188. We always round up because even if a page is half full, that means we need to allocate that page, or we need to read that page, we are rounding up always. Okay, so this will be around 188 pages total. This is the number of matching pages. Okay, for the result. So what should the cost be then? I come back here, it's the length of the height of the tree plus the number of matching pages. So here, if you give, I will actually, the correct answer in this case is, it should be directly 188, because if you assume that in your tree, you have a pointer directly takes you to the beginning. Because our condition doesn't have a lower bound, it has an upper bound, which means I need to start at the first SID value and keep reading until I reach the upper bound. But if you don't have this pointer, that means you need to come, read the root, go to the second level, read this node, go to the next level, and read the first page. That means you need to do 3 page reads to kind of reach the first leaf page, and then you need to do 188 or 187 additional page reads to retrieve all the data pages. That includes the matching records. And this will be around 192. So if you give me 188, 191, 193, I will accept those. One less, one more, doesn't matter in this case. Okay, depending on what you assume, it may be different. What I'm assuming is I'm searching through the tree, and then I'm reading all the data pages, needed data pages additionally. Okay? So, and we can multiply it by d. So this is kind of using numeric values forces you to understand certain things. It actually makes things more concrete. That's my purpose for assigning this question. What you need to do for part B is, now you will actually kind of, you know how to calculate the B value, how to use this information. Now you will actually repeat the same thing for the unclustered case. In the unclustered case, you are not storing the full tuple, you are only, since you are building the index on SID, you are only storing the SID value in the index. Your index entry size is smaller, that means your, you can fit in more index entries in the leaf pages. You will end up with less number of pages at the end, leaf pages in the index. But as you know, actually, search requirements are different for the range especially. Now you need to calculate number of matching records rather than number of matching pages. And as always, if file scan gives you a better cost than these costs, it will, database management system will always ignore the indexes and go with the file scan, favor the file scan, okay? Just do your best, kind of repeat the same calculations for the unclustered case, okay? Questions? So let me just maximize it so that you can see all of them at once. I expect, I mean, you don't give me the full detail, but I at least have, I expect this much kind of, you need to show the details of the calculation. So now what I would like to do is, this is an example that I will give you in your final sample. This is similar to your homework question, and I would like to cover it so that it helps you to complete the homework. What we will do is, given the schema and given some additional information, I didn't copy them over here. Let me, so example final. Given some additional information about the schema, you will find out, you will actually argue what indexes will help most to optimize the sum, given some queries that are frequently executed on the schema. So for this schema, we know that we are told that P&O is the primary key of project, MID is the primary key of manager. So also there is a foreign key that connects these two tables. Project manager is a foreign key referencing to the manager ID. So this value over here, this, okay, I cannot somehow do that. So this value over here is actually a manager ID, and it's a foreign key referencing to the MID. That's the actually only foreign key. But there is another attribute value which might be indirectly related among these two relations. This is a department name value. It specifies the department of the project or the project belongs to. And also managers have departments, which is not necessarily the same as the project's department. As a manager, actually, whatever kind of department you manage, you will be actually, that department will appear here in this table. Okay? So those are not foreign keys though. The only foreign key is from the project manager to MID. So, and also, this is important, the manager of a project need not to be employed in the same department. So, as a manager of, let's say, department 1, I may be involved in some project, but I don't necessarily need to manage that project as well, okay? Somebody else might be managing that project. So now we will actually look at these queries and we will suggest some indexes. So first one, for each of these, this is what I will do, and this is what I suggest you to do. This is really helpful. I'm going to write down the queries for each of them, the SQL queries, and then we will actually discuss what indexes can be used for those. Writing the query tells you, allows you identify the attributes very easily, the index attributes very easily. So if the first one says list the names, departments, and ages of the managers who earn more than 90K. So if I write it down quickly, I'm selecting from the manager table, okay? Only the manager table. I don't need to look into the project because it's not asking anything about the project. Where the salary is greater than 90K, and what I'm returning is the manager's name, the manager's department, and the age value, okay? So now, what index would you propose to speed up this query? Sorry?
Put it on salary.
Put it on salary, but what type of? So for each question, you need to decide on many things. Yes, the attribute. First of all, which table we need to put it, define it for? It needs to be for manager, right? There is no other table here. It needs to be for manager. What attribute? You mentioned salary. So what type of an index? Hash or B plus tree? Hash is terrible for the range queries because the values, consecutive values are not together. They may be all over the place in different buckets. It needs to be a B plus tree. And should it be clustered or unclustered? Clustered. Why?
Because you're gonna have to, otherwise you'll have to go into each page.
Exactly. Yeah. We will have a lot of employees, managers with the salary. For each of those, we need to go to the data page and retrieve their salary name, department, and age information as well. So this is clustered. So when you choose the clustered indexes or deciding on which index should be clustered, be careful because you can create a single clustered index. I mean, you are recommended, or database management system will force you to create a single clustered index per table because your clustered index will be your file organization, your data file. So now, I'm not writing the explanation, but in the exam, I expect one sentence explaining why you make these choices. One or two small sentences. You don't need to tell me the stories, I just want some justification. This is especially important in the homework. In the exam, I will be more understanding because it will be your own work. So, second one says list the names, ages, and salaries of the managers. Actually, you read through it and let me write down the query quickly to save time. Select the manager's name, age, and salary from the manager table again, and we look at the attributes, sex, and let's say it's female, and also the manager department needs to be some value, let's say it's EECS. Manager department, okay? So we are getting all the manager name, age, and salary of the managers who are females and who work in the EECS department. And it tells us that while there are many departments, each department contains only a few managers. This information is telling us something about the selectivity of this condition. That means this is not returning so many results. So what would you suggest in this case? So since it's not returning, this query is not supposed to return so many results. That means index definitely will be helpful because we are, rather than scanning everything and finding only a couple tuples, index will directly should take us to those tuples. So again, we need to do it on manager, right? And what attributes should we build the index on? The conditions are on manager department and sex attributes, correct? So, which means if I build the index on manager department and sex, that means I can quickly search the index for the matching ones, and it will be only a couple of them. I will follow the pointers, go to the data file, and retrieve them. Since there are not that many, I don't need to make so many page reads in the data file, right? So, how about the other way around? If I kind of swap the order, Is it better or is this better?
Because there's be more departments than there are male or female.
More departments, so you want to swap them?
No.
No.
I want this.
Yes, so sex is only female or male. So it eliminates by 50% in the best case. If it's the IT department, it's even less than 50%. If you are searching for males, it will be 80–90% of the department. So for the manager departments, so since there are not many managers for a department, probably one or two most, so this is pretty selective. Whatever attribute condition is more selective, it comes first. Okay, that's always the case. Selectivity is the most important thing you need to look into in the queries. So should it be a B+ tree or hash in this case? Both works, but probably hash is better because it's equality search. Okay, it will directly take us to the buckets, and there will be only a few of them. So should it be clustered or unclustered? Remember, we try to avoid clustered if it's not necessarily needed. Is it needed here, clustered? So there are only a few ones, that's tuples, that will be returned from this. It's not a big deal to actually go to the data page and read the tuples from the data page. So it will be unclustered in this case. Okay, clustered is not necessarily very important. So kind of the term for unclustered is usually sometimes non-clustered in some tutorials, just keep that in mind. So questions so far? Number 3, let's look at number 3. List the names, topics, and budgets of all projects with managers whose ages are in a user-defined age range. So now things are getting a little bit more complicated. Select, we are getting the project name, topic, and budget from the projects. And since this is a C project, and I will call this a P, and the manager, we need to look into the manager because we need the manager ages, manager as M. Let's actually put the P here. And we need to have a where condition piece, we need to do the join. The project manager needs to match the MID value of the manager, and also the manager's age needs to be in the range that is specified, needs to be less than 30. Okay, so since I need to access both of the tables, manager and project, and I need to join them, things are now a little bit more complicated. I need to consider the join as well and suggest indexes to perform to optimize the join. So for these kind of queries that has join, what I suggest you to do is first think about a reasonable query plan. Think about how database management system will solve this. Possibly it will look at one table first, retrieve the matching tuples, go to the next table. For each matching table record or tuple from the first table, it will scan through the second table and find the matching tuples to that. Okay, so here we have an additional condition on age. What do you think, which table it probably will look at first when it performs the join? Will it look at the manager table, retrieve the managers first, then look at the scan through the project table for the matching ones, or it will do vice versa, look at the project, scan through the project table, and then look at the manager table? So here, multiple things are important. The size of the table and what conditions, additional conditions are applied on those tables. So in this case, we have an age less than 30. This is a kind of young age for a manager. So, and possibly there might be, we have probably less managers compared to the projects, right? We may have tons of projects, but department managers probably are a handful or not as much as the number of projects. And further, we have this condition on the manager age. That means it will filter out certain managers already. That will be a smaller number of managers that we need to consider. So probably, I mean, this is again an estimate, not ground truth. It will first look at the manager table, find out all the managers that satisfy this condition. For each of those managers, look at the matching projects, the projects that that this condition is satisfied, and return these information about them. Okay? So that is, I make that kind of guess based on what I know about the data. So that means to kind of, we may suggest a index for managers first to optimize this range query, and then we can also actually suggest a index for the project table to optimize the join. Okay? So to optimize this range condition for the manager, what would you suggest? The range condition is on age. Age and MID. I totally agree with you, whoever said that. Who said it? Okay. So, because the condition is on age, probably we need to first include age here. It will quickly filter through those. And from the manager table, all we need is age and MID, nothing else. That means this gives me an index-only plan. Okay? So if I only included age, that might be helpful or might not be helpful, because still I had to retrieve MID. But since other thing that I need to retrieve from the manager table is MID, if I include MID as well, I will be able to do only index-only scan through the manager table. It will be, I don't need to look at the data at all. So this is definitely will help in this case. So should it be clustered or unclustered? Since it's index only, it needs to be unclustered. I don't need clustered in this case. And I already have a clustered index here that I propose, so I cannot create another clustered index. So unclustered, should it be B+3 or hash? If I use hash, will it work? This is a range condition. Hash doesn't work with range, so it needs to be B+3. Okay? So, for the project, now we are trying to optimize the join. For the project, what would you suggest in this case? What is the join condition on? Project manager, right? So I will take the MID value. This is the manager ID that has this condition on age. That satisfies the age condition. So given an MID value, I need to look at the project table. In the project table, the project MID value is project manager. So here, it's right here, project manager. So I need to quickly find the actually projects that has the same manager as that given MID value. So that means I need to build it on the project manager attribute. And should it be clustered or unclustered? I'm retrieving all these attributes, additional attributes for that project. And possibly, we don't know, there might be many projects for a given manager ID, right? A manager might be involved with multiple projects, we don't know. So, for now, I'm going to say it should be clustered because I still need to access the data to retrieve these additional attributes. And, but I will put a question mark next to it because I'm not really sure if the number of kind of searches, the number of searches that I will do on the project table is small, then clustered might not be necessarily needed. So I put a question mark, we will come back to this. So if I don't need a clustered index for the rest of the queries, I will keep it clustered. Otherwise, I will actually come back and change this to unclustered. And in this case, since this is equality search, I'm searching through the project table for a given manager ID, so it needs to be a hash, in this case will work fine. Okay? questions about that? So we move on, number 4. It says that list the departments such that a manager in this department manages a project based in the same department. So again, this is kind of one of the most kind of complicated queries in this list. We need to select the manager's department from both of the tables, from manager and let's say as M, let's give them names this time, project as P, and we will match the P's project base department to the manager's manager department, because we want to retrieve the projects that belong to the same department of the manager itself. Manager's manager department. And we need to also include the condition the project manager needs to be equal to the manager's MID. Project manager. This needs to be equal to the project MID. So here I'm matching both the departments and the MIDs. Okay, this is the join condition, but this is an additional condition that is actually specifically provided by the question. It says that department managers, the department's manager, the department of the project needs to be same as the manager's department. So in this case, we need to again do the same thing. I mean, we need to, since we are joining these two tables on two conditions now, we need to suggest indexes that will speed up both of those conditions, or it can be a single index or it can be multiple indexes. So what would you suggest? I'm just giving you, I mean, this may be probably the hardest one to come up with. And by the way, this example is harder than your homework question and harder than what I plan to ask for in the final. Okay, this is harder than all the other examples. So we don't have much time, and this may take, what I suggest to you is when you look at this, when I post the sample exam, just look at it without considering these solutions that I provided to you. Try to solve it yourself and be kind of double check. You will have more time to think about it. I'm sure you will be able to come up with something similar to what I provide. So for the manager, on the manager side, we need to, the information, the attributes that we need to access are the manager department, because that's actually what the join condition is, and the MID value. So if I provide an index on the manager department and MID, since those two are the only attributes, this will give me an index-only plan. Okay, that will be pretty efficient, and that means it can be unclustered. Doesn't need to be unclustered, and this is index only. And also for the projects, I can do something similar as well. I can actually suggest an index that will give index only plan, project base department, and the project manager. And again, these are the only two attributes that are needed to answer this query. This will give an index only plan as well. So for the index types, this one, we are assuming that, if we assume that we first look at the manager table, retrieve all the manager department MID values from this index, we need to have it as a B plus tree because we are going through all of them. And those will be in order of the manager department, which is the first value in the second index. So that might be helpful. I'm suggesting B plus tree, but hash might work as well here. Okay, so to keep it ordered, I'm suggesting a B plus tree here. So, and of course, we said that it needs to be unclustered. For the second one, since we do equality search, a hash probably will work better. We will be given a manager department, and we will actually search through this index to find the entries that is same as the department. So this will be hashed and of course unclustered. So just when you come up with indexes, just don't include so many attributes in the index and try to come up with index-only plans. Usually, index with more than 2 attributes becomes big. I mean, the more attributes you have, the bigger indexes you will have because your index entry size will increase. So try to avoid having large indexes. Sometimes having those indexes doesn't really help. So it needs to be only 1 attribute or 2 attributes. If it is possible to do it, come up with index-only plans with those kind of small indexes. That is helpful. Otherwise, it will have some additional trade-offs. So let's look at number 5 and 6 quickly. Hopefully we can finish those. For 5, this is a simple query. I'm not going to write it, but directly we will suggest the indexes. We need to list the project names and their departments with budgets more than 900K. So here only we need to look into the project table, right? We don't need to look into the managers. All information being asked is about the projects. So, and the condition is on the budget. We are looking for projects which are with budgets values greater than 900K. So, what would you suggest to optimize this? No join, it's simpler. What index is helpful in range? A clustered index on budget, right? So, budget clustered, and since it's range, it needs to be a B plus 3. So, did we create a clustered index on budget before? Sorry, on project before? So here we had this one, projects on project manager, and we said that we are creating a clustered index in this case. So we cannot have clustered for both cases. So here you have 2 options. Either you can come back here, either get rid of this index and say that, okay, I'm not creating an index, I'm kind of sacrificing from the performance of this query, and I'm removing this index, or I'm making it unclustered, and that will be probably less efficient than the clustered one, and then you can make this one clustered, the second one, the one in number 5 clustered. Or, if you look at this query a little bit more carefully, it says that list the project names and their departments with budgets more than 900K. So, again, even though it's not actually very much suggested, if you create an index on the budget project name, and let me erase this one, and the project base department, name and project base department. So this will give me an index on the plan. So this is a larger index. Now you need to actually think about the trade-off. If this other query, the one that I chose here, is really important, if I don't want to sacrifice from the clustered index, then I can actually introduce this large index and be able to optimize both of them. If the other one is not important, I can use a clustered index only on budget here and remove the other index, okay? So these are the decisions that you need to make. You need to kind of look at the trade-offs. It depends on the application, it depends on the data, it depends on what queries are more important. What I'm trying to teach you here is being aware of these details and be able to make those decisions, okay? If you explain them well in the homework or in the exam, I will accept both answers. There is no ground truth in this case, okay? So I'm keeping it like this. This will be in the sample solution as well. We keep the other one clustered, and I'm making this one unclustered, and we are using an index-only plan in this case. So I will quickly talk about 6. I will give you the solutions for these anyway later. For number 6, you need to list the name of